Welcome to 1.1, the real number system. We have 4 objectives for this section. We're going to be understanding the set of real numbers and the subsets of those real numbers. We're going to use the real number line to order real numbers. We're going to find the distance between two real numbers, and lastly, find the absolute value of a real number. So in each of these objectives, you hear the term real number. Well, we kind of want to define that and understand what it truly is. So a real number is basically any number you use in everyday life. Okay, so there's 2 categories of numbers. Those numbers that you use in everyday life, those are called real numbers. Basically, any number that you can think of is a real number. And then there's this other category called imaginary numbers. Okay, so we have real numbers and we have imaginary numbers. Imaginary numbers, we're not going to get to until second semester. Okay, so we're not really concerned about these yet, but they're there. I just want you to know they're out there. They're not real, they're imaginary, like the ghost under your bed. So in real numbers, we have some subsets. Okay, so different categories broken down. The first category I want to talk about is rational numbers. Rational numbers is any number that can be written as a fraction. Okay, so those numbers include, well, obviously any fraction like 2/3, 7/8, but also 0.3. Remember, because this is the fraction, this is the same as 3/10. It can also be negative 3.125. That's written as a fraction. We could have 0.4 repeating. 0.4 repeating is 4/9 as a fraction. Okay, so a couple things that I notice about this group of numbers is I notice that it can be negative. Okay, it can be a decimal. It can be a positive number. It can be a fraction. And specifically looking at the decimal numbers. So I have 0.3, negative 3.125, and I have 0.4 repeating. Well, what I notice is that I have a repeating one. It's 0.4, it goes on forever and ever. I have a terminating one, it's just 1, 2, and then 5, and then it quits. And then I have a terminating one here, it's just a 3, and it quits. So rational numbers can repeat, and they can go on forever. But what rational numbers can't do is go on forever without a pattern. Those numbers are called irrational. Now remember, these 2 categories, rational and irrational, they're still a part of the real numbers. Okay, they're both real numbers. They're just 2 different categories. So some examples of irrational numbers, first let's define it. It's numbers that go on forever with no pattern. Okay, it never repeats itself. So 4 repeated itself. It went on forever, but it repeated itself. So that's still rational. So some common irrational numbers would be pi. Pi is 3.141529, yada, yada, yada. It goes on forever, and there's no specific pattern to these numbers. Another example would be the square root of 2. If you type the square root of 2 into your calculator, you get some decimal that goes on forever, and it never repeats itself. While we're talking about square roots, I want you to be careful with square roots. You might be tempted to think that all square roots are irrational, but that's not true. Most of them are, but some of them aren't. For instance, what if I had the square root of 25? Well, if you type that in your calculator, that's just 5. That's a rational number. That's any number that can be written as a fraction. 5 as a fraction is 5/1. Okay. So irrational is a very slim category. Rational numbers can be broken down even further. So within the rational numbers, within all of these numbers that I've listed, I have another category, the integers. So integers are part of the rational numbers, which are part of the real numbers. So integers are also real numbers. You may have heard this term before, but an integer is positive and negative. I call them normal numbers. That's not really a math term, but it helps me remember what an integer is. It's positive and negative normal numbers. So for example, -1, 0, 5, 1,000, -126. So any positive and negative number that's not a decimal, it's not a fraction. It could be disguised as a decimal or a fraction, such as 3.0 or 6 divided by 2. So 6 halves is actually just 3. That's an integer. So be careful on some of the fractions. If you can reduce it to an integer, a normal looking number, then make sure you lump it in that integer category. Okay, so within the integers, we have this next set. That we call whole numbers. And whole numbers are positive numbers and 0. Okay, so it has to be part of the integers now. Whole numbers are part of integers. So look at some of these integers here. They're the positive ones and 0. So basically, now let's write in the definition here. Positive integers and 0. So we include 0, and then obviously 1, 2, 3, all the way on up as high as you can count. 153, yada, 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 100,000, yada, yada, yada. You get the idea. So the positive numbers and 0 is whole. Then we can break the whole numbers down. So within the whole numbers, there's another category, and those numbers are called natural. They're called natural numbers because it's natural to count. So I call them, they're also known as the counting numbers. Now, if I said count the green circles up here, you would go 1, 2, 3, 4. Those are the natural numbers. And it goes on forever and ever and ever. What is specific about natural numbers is you don't have 0 in the natural numbers. You don't, when you start counting, you don't start from 0. You don't say this is 0, 1, 2, 3 circles. It's 1, 2, 3, 4 circles. Okay, so the counting numbers would be 1, 2, 3, dot, 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 all the way up to whatever you want, 227 or a million. Okay, so they go on forever, the natural numbers, but what's important is it does not include 0. So they're the counting numbers. I'm going to put in parentheses, not 0. If you have any questions about this chart, please come and ask me. What I want you to know is that rational, integers, whole numbers, natural numbers, and irrational, they are all part of the real number system. Okay, they're numbers that we use in everyday life. I use pi every day. I use 2/3. I use 3, 227, -3.125. They're all real numbers. Okay, it's just broken down. How I like to think of it or explain it sometimes is that like real numbers is like Major League Baseball. And within Major League Baseball, you have 2 categories maybe. You have the the American League and you have the National League. I hope I did this right. Within the American League, then you have Maybe, oh gosh, I don't know how Major League Baseball works. Maybe you have West. So the teams in the West, maybe, oh, correct me, I'm probably wrong, but Kansas City Royals. And then within the Kansas City Royals, then you have Mr. Perez here. Okay, Mr. Perez, he's still part of the Major League Baseball. He's just in a lower subcategory. He's part of Kansas City Royals. Kansas City Royals are part of the West, and the West is part of the American League, which the American League is part of the MLB. So it just breaks it down into simpler and simpler categories. But American League and National League, they're still part of the MLB. So rational and irrational are still real numbers. Hopefully that illustrates better what is going on in this diagram. All right, so classifying real numbers here. So we need to decide what category these numbers go in. Now remember, they can go into more than one category, such as this number square root of 25. It's a rational number, but it's also an integer. It would also be a whole number, and it would also be a natural number. So let's start with the natural numbers. Remember, those are our counting numbers, so anything from 1 on up. So not -7, not negative square root of 3, not -1, or -1/5. What about 0? Is 0 part of our natural numbers? So I go back to my category, natural numbers. Oh, not 0. Then I have 3/4, nope. Square root of 2, no. Pi, and then I have 5. So my only natural number here would be 5. So I'm going to put 5 in these brackets because it is a set notation. These brackets mean a set. So the set is just the number 5. Now let's go to integers. So integers can be positive and negative normal looking numbers. So for instance, I have a -7. Negative square roots of 3. If I typed that in my calculator, square root of 3, I'd get a funky decimal. So that wouldn't be an integer. Then I have a -1. And I have -1/5. Can an integer be a fraction? So I go back and look at some of my examples. Well, it can be a fraction as long as that fraction reduces to a normal looking number. But 1/5 wouldn't reduce at all. Then I have 0. Is 0 included in my integers? Yes, it is. I'm going to put 0. 3/4 doesn't reduce. Square root of 2 is a decimal. Pi is a decimal, and then we have 5 would be a normal integer number. So there's 4 integers in this set. Next is the rational numbers. So let's refresh our memory on a rational number. It's any number that can be written as a fraction. Okay, let's look at our set here. Well, obviously, oh, wrong way. Rational numbers include integers, whole numbers, and natural numbers. So we've already done integers and we've done natural numbers. All of those numbers in that set of natural and integers can fit into rational. So let's put -7, -1, 0, and 5. Those are rational numbers. Remember, they're part of the American League. It's the people in the West Conference, like Perez. They're still part of the American League. Okay, so let's look at our other numbers. What about negative square root of 3? Would that be rational? Well, if you type, like I said, type square root of 3 in your calculator, and you get -1.732050808, and it looks like it goes on forever without a pattern. So that wouldn't be a rational number. Now I have -1, that's included. -1/5. Oh, that's a fraction. 0, we already included. 3/4, that's a fraction. Square root of 2. Remember, if we type square root of 2 into our calculator, we're getting something like 1.41421356. It goes on forever without a pattern. That's not rational. And neither would pi. Pi is 3.141529, yada, yada, yada. And then we had 5 included. So irrational. Irrational are all of the numbers that aren't rational. Okay, so anything that we didn't list in the rational we're going to put in the irrational category. It's one or the other. So there were 3 numbers that we did not include in the rational set. We did not include negative square roots of 3. We did not include square root of 2. And we did not include pi. Those are our 3 irrational numbers. Now I want you to practice this one. So pause the video and fill in A, B, C, and D based upon this set of real numbers. All right, so I have the filled in answers here, and something I want you to keep in mind that the rational and irrational are the 2 categories that make up the real numbers. Rational and irrational, the 2 main categories. So these 2 sets here need to equal the amount of numbers in this set up here. So I have 1, 2, 3, 4, 5, 6, 7, 8 numbers, and then added with these. So I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're good. The rational and irrational make up this set of real numbers. So check your answers with mine and see how well you did. Next, we want to talk about the real number line. This picture represents a number line. You've all seen a number line. The origin is 0. Okay, and then we have numbers to the left of 0. Those are our negative numbers. And numbers to the right are our positive numbers. 0, I want you to remember that it's neither positive nor negative. Okay, so sometimes we call that a non-negative. Non-negative refers to positive numbers and 0. Okay, so plotting real numbers. It gives you 4 numbers here that I want you to plot on the number line. So I'm going to draw one with 0 being the origin. And then I'm just going to go 1, 2, and 3, and -1, -2, -3. So just going to be a rough sketch, but let's plot part A, -5/3. So I know that -5/3, if I type that in a calculator, that's going to be -1.6. And sometimes it helps to see the decimal when we're going to plot it. But I know this number, it lies between -2 and -1. So somewhere in this section. But it's a little bit closer to -2. Okay, so I'm just going to plot it a little bit closer to -2, and we'll call this point A. Next, B is 2.3. Now that's already at a decimal, and I know that decimal lies between 2 and 3, but I know that it's a tad bit closer to 2. So we'll call that point B. Part C is 9/4. 9/4, if I represent that or write it as a decimal, it's 2.25. 2 1/4. 2.25 lies between 2 and 3. It's closer to 2. And I want you to notice that we've already plotted the point 2.3. So we have 2.3 and 2.25. So 2.25 is less than 2.3, so it needs to be closer to 0. So I'm going to put that point right here, and we're going to call it C. And lastly, I have this point D is -0.3. So 0.3 lies between -1 and 0, but it is a little bit closer to 0. So I'm just going to smudge it a little bit closer and call it D. So you all know how to plot. I just want you to go slow on it. It may seem like something easy, but the easy problems are the ones that are easy to mess up on. So take your time when plotting points and really think about it. Maybe convert fractions to decimals. And don't get fooled by the negatives. I want you to practice. So draw me a number line and plot these numbers. You could do separate number lines. And plot for me these 4 numbers. All right, your graph should look like mine. So 3 is an easy one. Just plot it at the hash mark 3. 5 halves is equivalent to 2.5, so it goes halfway between 2 and 3. Negative 7 halves is equivalent to negative 3 halves, so it goes halfway between the negative 3 and the negative 4. Then we have negative 5.2, so it's in between negative 6 and negative 5, but it's a little bit closer to negative 5. Okay, now ordering. Ordering is easy when we know how to plot on the number line. So let's look at this notation here. What does that mean to you? Some people might say it means A is less than B. Is there another way to read that? It also means that B is greater than A. Okay, so you might have learned in, I don't know, elementary school, I don't know what grade, but this symbol, since it's like an alligator mouth, and an alligator always eats a bigger number. So which number out of A and B is bigger? B is bigger because this mouth is chomping down on B. Okay, so B is greater than A, which means that A is less than B. Then they try to get complicated on you in elementary school, and they put this line underneath the inequality symbol. What does that mean? Well, this line underneath means that it could be or equal to. So this could be read as A is less than or equal to B. It could also be written as B is greater than or equal to A. Okay, notice how the alligator mouth is eating B here, and the alligator mouth is also eating B here. Nothing has changed. These two problems are the exact same. They're equivalent. They mean the same thing. But what's not equivalent is this. The alligator mouth is eating A here, and the alligator mouth is eating B here. Not equivalent. So let's talk about actually ordering numbers, because it's simpler than this chart makes it seem. I just wanted to give you a backstory on inequalities and how they worked. Okay, what's the exact same inequality or ordering that I could write with B first and A second? Well, the same as this. The alligator mouth would have to be opening towards the A, and then it's an or equal to symbol. The same as this, with A first and B second, would be the alligator mouth eating the B. So it wants us to place the correct inequality symbol in between these two numbers. So we have 4 inequality symbols: the less than, the greater than, less than or equal to, and greater than or equal to. Okay, inequality. We also may use equal in the future, just so you know. All right, so negative 4 and 0, which one is bigger? Well, bigger numbers, if we're talking about the number line, are off to the right. So bigger numbers are on the right, smaller numbers are on the left. So if you were to place negative 4 and 0 on the number line, you'd have negative 4 here and 0 here, which means 0 is bigger. But we all knew that. Negative 3 and negative 5, this one may seem a little bit more complicated, but think about your number line. 2, 3, 4, 5. So here would be negative 3, and here would be negative 5. The one furthest to the right is the bigger number, so we want the alligator mouth eating the negative 3. 1/5 and 1/3. Same thing. You can think about a number line if you want. You'd have 0. They're both positive numbers, so they're on the right of 0. And they're not quite yet up to 1. You would have 1/3 here and 1/5 closer to 0. So 1/3 is the bigger number. And then we have negative 1/4 and negative 1/2. If you don't already know, I highly suggest drawing a number line. We have 0 and -1 because they are negative numbers, so they're to the left of 0. -1/2 would be right in the middle. -1/4 would be closer to 0. So which one is bigger? Well, the one on the right is going to be bigger. So we want our alligator mouth eating the -1/4. I want you to practice. I want you to pick 5 here, any 5 of your choice, but one of them has to be number 15. So pause the video, make sure you do number 15, and then pick 4 more. All right, check your answers with my answers that I put up here. Let's talk about number 15. If we wrote these as decimals, -10/3 would be -3.3 repeating, and -2/3 would be -0.6 repeating. So on a number line, if we think about which one's furthest to the right, and here's 0, here's -1, -2, and -3. -3.3 repeating would be off over here, and -0.6 repeating would be somewhere in here. So the furthest to the right would be -0.6 or -2/3, which is bigger. So we want the alligator mouth eating the bigger number. Okay, finding the distance between two numbers is exactly what it sounds like. So if we're on a number line, and just for an easy example, what is the distance between 1 and 2? Well, it's 2 units away. Now it gets more complicated when we have negative numbers or we have fractions. So I want you to use this rule. Anytime you find the distance between two numbers, what I want you to do, if the numbers, let's just call them A and B, you take, well, let's say, using our same notation, that A is less than or equal to B. So that means B is the bigger number. If you want to find the distance, then you subtract the big number minus the little number, B minus A. So if you want to write that in your own words, big, minus little gives you distance. Now the reason we do big minus little is because distance always has to be a positive number or 0. Okay, I can't be -12 feet from a person. I'm 12 feet no matter where I'm standing from them. Well, as long as it's 12 feet. In any direction though. Okay, so let's find the distance between these real numbers. We have -2 and 3. Well, you can do it the old-fashioned way, and you could do a number line. Here's 0, -1, -2, 1, 2, 3, and they're going to be 1, 2, 3, 4, 5 units apart. You could do it that way. Or you could take the bigger number, 3, minus the smaller number, -2, and see what that is. So we have 3 minus a -2. Now I want to talk about this now, even though we're going to talk about it in the future. Negatives and what they do to a problem like this. So when I see this subtraction sign, and I'm at 3 here, so it's 3 minus -2. Well, minus means to go backwards, right? And negative doesn't necessarily mean to go backwards, it means change direction. So instead of going backwards, we're going to change direction and go the amount of spaces that this number is to the right. So we're going to go 2 to the right. We're at 3, now we're at 5. Let's look at another example. -4 and 0. I want to take the bigger number, so 0, and subtract the littler number of -4. So if we're on a number line and we're at 0, subtraction means to go to the left. However, the negative means change direction. So if we're going to the left, now we need to go to the right. So we're going to the right 4 units, 1, 2, 3, 4. That means we are at the number 4 and the distance is 4. Or you could just do it the easy way and type it in your calculator. 0 minus, and then hit the negative button, and then hit 4, and it's going to spit out the number 4 for you. Okay, so 0 and 4, that one's kind of easy because if you think about a number line, they're going to be 4 units apart. Then we have 1 in negative 1/2. So let's do our algorithm of big 1 minus the little minus negative 1/2. You could either type that in your calculator or you could use my thinking process. So if we're at 1, negative typically means to go backwards to the left, subtraction means to go backwards to the left, but negative means, oops, stop what you're doing and change direction. So now we're going to the right. So we're at 1, we're supposed to subtract and go to the left, but this negative says change direction, and now we're going to the right 1/2 units. And we end up at 1 and 1/2. So distance, notice, is positive numbers for these answers, positive numbers. It could be 0 though. What's the distance between 5 and 5? That distance is 0. You don't move any at all. Okay, absolute value is our next topic. It is the last objective that we're going to talk about. Using that idea of distance, I want to first talk about the term opposites. So for instance, two numbers are opposites if they're the same distance away from 0, but on opposite sides. So for instance, on our number line, we have 0 here, and then we have a positive 1 and a negative 1, both of which are 1 unit away from 0, and they're on opposite sides. So negative 1 and 1 are opposites. So likewise, negative 11 and positive 11 would be opposite. So it's just the negative and positive version of a number. Now what happens when I add negative? So if I have a number, let's call it A, and I add it with its opposite, negative A. Well, that's going to give me 0. So for instance, if I have 9 plus a negative 9. Okay, you're on your number line. Here's 0, here's 9. We're at 9. Add typically means to go right, but this negative says, just kidding, you can't go right. Change direction and go left 9 units. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we're back at 0. Okay, so negative means change direction on the number line. So anytime you're adding opposites, you get 0. That's called the additive inverse property, which we'll talk about more later. This idea also connects with absolute value because the definition of absolute value is the distance a number is from 0. So how far away is negative 1 from 0? Well, we said that's 1 unit. How far away is 1 from 0? That's also 1 unit. Okay, so something important is absolute value, it will always, I shouldn't say always, I should say always. It will always be a negative number. Or excuse me, positive. It will always be a positive number because remember what we say about distance? Distance will always be positive or 0. And absolute value is the distance. Okay, so we talked about what it means. Let's talk about its symbol. So we have 2 big bars here. Let's say we want the absolute value of 7. So we put 7 in these bars. How far away is 7 from 0? Well, it's 7 units. Okay, what if I took the absolute value of the opposite? So the absolute value of negative 7. How far away is negative 7 from 0? Well, it's also 7 units. Notice how the absolute value becomes a positive answer. Gets a little bit trickier though, like on part C. What if I have a negative absolute value of negative 6? Well, we'll jump to that one later. Back up top, A and B, I want you to pause the video and find the absolute value for me. Okay, so for A, you should have gotten 10 because the absolute value of negative 10 is positive 10. It's 10 units away. Absolute value of positive 3/4 is 3/4. It's 3/4 units away. Now let's get to C. So let's first deal with the absolute value symbol. Okay, so inside our absolute value is what we're looking at, negative 6. What's the absolute value of negative 6? How many units away is negative 6 from 0? And it's 6 units. But we still have this negative out in front. Okay, so I just found the absolute value of whatever was inside, and the negative out in front means my answer is negative 6. So the answer isn't positive, but this absolute value portion, it was positive. I just had a negative out in front. So don't let that fool you. Take your time on those. Let's use this absolute value property to help us compare numbers. So again, it's the less than, the greater than, or possibly equal to. So I have the absolute value of negative 2 compared to 1. So what I first want to do is simplify my absolute values. The absolute value of negative 2 would be 2. Now I'm comparing 2 and 1. It's the exact same problem. Well, the alligator eats the bigger number, so it would eat this 2, which means that my final answer would be the absolute value of negative 2 is greater than 1. Over here, let's take care of or simplify our absolute values. So the absolute value of negative 4 would be 4. The absolute value of 4 was 4. Therefore, I put an equal sign in between here. Over here, simplify 2 and simplify this. Remember, we want to just look at the inside of our absolute value. The absolute value of negative 2 would be a 2. Drop down our negative. Now let's compare which one would be bigger. 2 is greater than negative 2, so alligator mouth eating the 2. I want you to pause the video and go ahead and practice these 4 problems. Evaluate the absolute value. All right, go ahead and compare your answers with my 4 answers. And let's talk about translating words into symbols. Remember, we're going to write each statement using inequality symbols. So we have less than, greater than, less than or equal to, or greater than or equal to. So the first one says the price P is our variable, is less than $225. All right, so I know I have P. I know I have 225. Remember, we want it to look something like, I guess I don't have an example. We want it to look like an inequality, such as, let me see if I can find one, such as these examples, except instead of 2 numbers, I'm going to have a variable and a number. So I have a variable P, my number is 225. Now let's use the context clues to help us fill in which of the 4 inequality symbols we need. P needs to be less than 225. So I want the alligator mouth eating the 225 because P needs to be less than, it's smaller than. The average A will exceed 5,000. Okay, so let's start with A. Let's start with 5,000. Now I have a 25% shot of getting this right. A, just think of it as a number, is going to exceed. What does exceed mean? It means greater than. So A has to be greater than 5,000. Can A be 5,000? Do I need to put an or equal to here? I don't think so because exceed means it must be more than. All right, let's check 3. The tire pressure P is at least 30 pounds. There's at least, that's a keyword, per square inch, and no more than 35 pounds. Okay, so how can I have 2 numbers and a letter? Well, think back into algebra. We had things called compound inequalities. They were 2 inequalities smushed into 1. So I'm going to first write this as 2 separate inequalities, and then I'm going to combine it into a compound. So let's start with the 30 pounds. So I have P and 30. P is at least 30 pounds. The pressure of this tire is at the smallest, at the least amount, 30 pounds. So do we want the pressure to be under 30? No, because 30 is the smallest it can go. So we need that pressure, P, to be bigger than 30. Can it be 30? Do I want to put an or equal to here? At least means it can be 30. It can be 30, but that's the smallest we'll go. Okay, so there's one. P is greater than or equal to 30. Now let's work with the one with 35 pounds. Okay, the pressure can be no more than 35. No more than. So can the pressure be bigger than 35? No, because we can't be more than. So the pressure needs to be less than the 30. Can it be 35? It just says no more than, but doesn't say anything about we can't be 35. So I want to put that or equal to there. It's 35 or less. Okay, so those are my two inequalities. How do I put them together into a compound one? Well, I want to put P in the middle, my smaller number, and then my bigger number, just like a number line. And then I want to make sure I fill in with the right inequality symbol. So I've already written it over here. When it's dealing with the 30, the alligator mouth is eating the P. Okay, so look at the 30 and the P. I need the alligator mouth to eat the letter P and not the 30. So I need it to open this way. And don't forget there's a line underneath. Now when I'm talking about the P and the 35, the alligator mouth is eating the 35. So over here I need the alligator mouth to eat 35, and that's the less than or equal to symbol. So this is my final answer. This is my compound inequality. The pressure is at least 30 at the smallest and no more than 35. So P, the pressure, is somewhere in between 30 and 35. All right, the last one. A bicycle racer's speed, S, is at least 16 miles per hour and at most 28 miles per hour. So our bottom number is 16. Our top number is 28. Can it be 16? Yes, it can. That's the smallest number it can be. Okay, so S needs to be bigger than or equal to 16. And at most 28 miles an hour. Well, that means that we can't be more than 28. It can't be S, the speed is bigger than 28. That's not what we're saying. We're saying the speed's got to be smaller or equal to 28. So some students get confused. They see this part and they see it opening towards the 28. So they think that that means bigger than 28. No, this is saying S is less than 28. The speed of the bicycle is not getting bigger than 28. Please, if you have any trouble with these at all, please, please, please ask. I'm here to help. Okay, I need you to practice these 4 examples. So pause the video. This is the last slide we're going to do, and try your very best. All right, check your answers with mine, and just to be clear that all of these were or equal to, they all have a line under them. Okay, so on the roller coaster one, you can still be 52 and get on the ride, so that's why it's X, the height, can be equal to 52. It can also be greater than. Okay, so when it doesn't give you a variable, you get to pick your variable. I used X. You could have used C for a coupon, or H for height, or M for minutes, whatever you wanted to use. The variable doesn't matter, but your symbols do. Remember that you could have also written this with 2 first and X second, just as long as the alligator mouth is opening up towards the 2 in both of them. And same thing down here, the alligator mouth needs to be opening up towards the X, otherwise it would be wrong. And the same goes for your compound inequalities. Remember, if you have any questions, please, please, please don't hesitate to ask. I am here to help you. Pause the video at any time during this notes and help or ask for help. Just know that these videos aren't replacing me teaching. Go back and listen to a video if you're having trouble with a particular part of the homework. That's the beauty about these videos, is they're up there forever. That way you can go back and review.